The theory of plate tectonics has to be the most significant contribution in 50-year history. This one theory has changed how we look at the Earth. I mean, there are things that we have seen and observed for centuries that we thought we understood, but we really didn't. Now we understand them. There's still some things we don't, but nevertheless, there's so many things we understand now that we never did before. Now, it sounds pretty hairy, but it really is not. What this is really it's all about is continental drift, the idea that the continents are moving around, which is sort of an interesting idea. Now, to get started, we have to go back to our discussion of that transition from the protoplanet Earth to planet. Segregation of the core, and then the layer above that, which is called the mantle, and then finally the outermost layer, the thinnest layer, the lowest density, aptly called the crust of the Earth. Now, what you have to picture now, in these early days, lots of molten things are going on down there. Molten rock. Below the surface, we call it magma. Once it comes to the surface, we call it lava. So the difference between lava and magma is simply location. Now, you're going to find out throughout the course, eventually, there are three kinds of magmas. There are granitic magmas, andesitic magmas, and basaltic magmas. Now, the names we apply refer to the kind of rock that forms when they solidify. Now, we're going to talk about the granitic and the basaltic here. Granitic magmas form granites. You know what granite is, tombstone stuff. The basalt, if you've ever been to some place like the Hawaiian Islands, it's 100% basalt. So a lot of you have seen basalt. Any lava flow that you ever saw in the world, I can guarantee you that it was a basaltic lava that froze up. So anyway, these two magmas, now they're totally different in composition, but for our discussion here today, the big difference in composition is the amount of silica dissolved within the magma. In the case of the granitic magma, we're talking probably 75 or 80% silica. Whereas in the basaltic, it's only about 45%, a big difference. Now, all you have to understand is the more silica you have, the thicker and stickier it is. Viscous, the more viscous. So the idea is that granitic magmas are very, very, very viscous, and basaltic magmas are the lowest viscosity of all. Now, I would compare it, I like to give things you can sort of picture in your mind. If I were to get a model for those two, for the basaltic magma, I might pick olive oil, and you see the sort of viscosity we have there. For the granitic magma, molasses, after you've kept it in the fridge for about a day. So you get some feeling for the difference of these two. So picture now, down within the Earth, these molten masses of basaltic magma and granitic magma rising toward the surface. Now, because the basaltic is so much less viscous, it rises very, very fast, reaches the surface first. Now, picture now, very low viscosity, so it can actually run like water. Well, you've all seen pictures of the eruption in Kilauea on the Big Island of Hawaii, and you've all seen the river of molten rock heading down to the south shore. That gives you a picture of what basaltic lavas are like once they spew out on the surface of the ground. So anyway, this stuff came to the surface long before the granitic stuff, and now since it runs very readily, it did indeed flow out and completely enclose the layer below, which we call the mantle. So we have then this layer of basaltic lavas, and whenever they solidify, we still call it lava. I don't know why we didn't pick another word, but we didn't. Anyway, so we have this layer of basaltic lava, thin, maybe averaging about 5 miles thick, which to a geologist is relatively thin, you see. So we have this layer now of basaltic lava at the surface, still molten, still erupting, and then finally the granitic stuff makes it. Now the granitic stuff, when it gets to the surface, it's thick and sticky. It doesn't like to flow, so all it does is sort of pushes the basaltic stuff out of the way and forms these big blobs of granitic rock, which finally forms sort of islands, if you will, surrounded by this sea of basaltic lavas. Now, in the beginning now, you have to remember, picture this now, this is to the surface and erupting, new basaltic lavas, new granitic lavas, and so it was a very, very volcanic place. One of the things you're going to learn when we take up volcanoes is the number one gas emitted from all volcanoes is water vapor. Interestingly, where did it come from? Back in those primeval days, all those comets, that frozen water coming in, most of us geologists believe that the source of the water we see on Earth today were the comets that came in that primeval state. But anyway, belching out all of this water now. Now, the surface is too hot to have the water lay down there in a pool, so it evaporates into the atmosphere. So here's the picture you want to have of this primeval time now. You have completely enclosing the Earth a thick cloud cover, much like Venus does today, except remember hers now is carbon dioxide. Ours is water. And so the picture you have of what the Earth's surface must have looked like, a very eerie place, molten rock coming to the surface, red hot, flowing, erupting, and no light coming from the sun. I mean, the cloud cover was so thick that no light could get through. So it would have been a very, very gloomy place had it not been for that molten rock, lighting the bottom of these clouds. So if you picture these clouds, though, sort of cherry red or rosy red with this molten rock down below, a very, very eerie scene. As a matter of fact, I'm sure you've seen, here's a little bit of trivia for you, full-length color cartoon movie by Walt Disney, of course, I believe it was 1940. Fantasia, that was one of the vignettes in Fantasia, if you remember back to that one. So anyway, sooner or later, things started to cool off. Sooner or later, the surface of the Earth cooled, enough so that the rains could come and fall and stay. And it rained, and it rained, and it rained for a very, very long time. The rain ran off the highs into the lows and filled the lows, which became the ocean basins. And so now we have the ocean basins underlaid by basaltic lava. Rising above them is sort of super islands. You have these granitic masses we now call the continents. Well, you know, I think geologists still sort of think that's the way everything formed. And when did all this take place? I think most geologists would believe that the crust that we call the granitic crust and the oceanic crust, all that was probably formulated within maybe 3.5 to 4 billions of years. So you're back in that sort of time scale. Well, that's still what we teach today. But here's something else they taught. Now, this goes back even before the days of geologists. I mean, there were earth scientists looking at Earth before geology ever came onto the scene in about 1750. And what was taught was the size and the shape and the locations of the continents as you see them today, that was created back then 3.5 billions of years ago when all this took place. In other words, if you had a map or a globe of the Earth then and a map of the Earth today, they would look basically the same. Well, that was okay for a while. Then about what would be maybe the 1400s or the 1500s, map makers started making maps that had the continents outlined, not as well as we do today, of course, but at least outlined to the point where you could start to see some similarities or dissimilarities in what the coastlines look like. And the one that just stood right out, and I'm sure you've all seen this, is the similarity between the Atlantic coastlines of Africa and South America. They look pretty much the same. And I'm sure there were a lot of individuals looked at that and wondered, I wonder, were they ever together? And the reason why they look the way they do is because they broke apart. And the Atlantic really formed. It wasn't always there. It actually formed. Could that be possible? And I'm sure they went to these early Earth scientists, posed the question, and I'm sure the early Earth scientists said, no, it's not possible. The way you see the continents today, that's where they've always been. But yeah, but look at the similarity. Well, I know, I've seen that too. It's pretty similar, but that's not the idea. They were formed that way. But gee, that's just too much to be fortuitous. Well, yeah, all right. You want to put them together? Is that what you want to do? Well, yeah, that's what we had in mind. Okay, you put them together. Okay, you got them together now? Well, yeah. All right, now you answer me the question. How are you going to get them apart? Where are you going to get the energy to do that? We're talking ripping continents apart here, people. Where are you going to get the energy? And they couldn't come up with the answer. They simply said, well, we thought you would tell us. No, I don't have to tell you that because I never thought they were together. So here's the point, you see. The point is, all those people who thought that these continents were once together, they couldn't come up with the way they got apart. See, if you're going to put them together, you're intellectually required to get them apart. They couldn't come up with two things. Number one, where are you going to get an energy source big enough to do it? And even if you could find it, Where's the mechanism that you're going to apply with that energy to cause the tensional forces that's going to be required to rip a continent apart? They couldn't do it. So that's the way it stood for a long, long, long time. All these people trying to answer that question, they never could come up with that energy source or a mechanism. Then onto the scene came a few people. There was a guy named Edward Zeus. I don't think he was any relative to Dr. Zeus. But anyway, this guy saw that, and he actually said, I don't care what you guys say. He put them together, and he was the one that coined the name Gondwana. You'll see Gondwana a lot on these old maps. Gondwana was indeed the union of South America and Africa. He was the one that coined that name. But the guy who came onto the scene that really got the ball rolling and should get the credit for a lot of this stuff was a guy by the name of Wegener, Alfred Wegener. Wegener was a German geographer, actually, and I don't know if this is a true story, but it makes a good story. The story goes that he was a soldier in the First World War in the German army, had been wounded, recuperating in an army hospital, was looking at these maps, that he had seen that for years, but he went one step further. He cut the maps out, put them together, and if you cut them out, here's an important point now. If you cut them out at the shoreline where the water meets the land, the match is really pretty good. It's about 80-85% good. But I think most of you know that's not really the edge of the continent. The continent actually goes out under the water a bit before it drops off into the ocean deep. We call that the continental shelf. If you make your cut at the edge of the continental shelf and put that match together, all of a sudden it's about 90+% good. So he was absolutely convinced. I don't care what these geologists say. There's no doubt in my mind these were once together. And then he wanted to see how far he could go. So he just basically got all the continents and put them all back together again. And he came up with a supercontinent called Pangaea. So in his mind, there was once a supercontinent called Pangaea surrounded by a super ocean. And then what happened? According to his idea, what happened about 200 million years ago, and that's sort of an important number too, you might keep in mind, about 200 million years ago, it broke up and all the pieces moved away and became the continents we now see today. Well, he published that paper in about 1915, not well received by the geological community. Not well received. First of all, if they even considered the possibility that he was right, then they would have had all the continents forming back there 3 billion years ago. That wasn't right. And then, of course, you're going to say, okay, you lied to us then. What else you lied to us about? So no one wants to admit a mistake that big. So anyway, no one believed him. And he took a bad hit. There were not very many people who were willing to side with him and become advocates. But there's always, of course, a few disciples who are going to keep the thing going. But I remember when I took my first course in geology, and the matter of fact, I was a chemist, remember? One of the reasons why I got into geology is because I read this article on continental drift. And I thought that was wild. Continental drift? There's nothing like that kind of stuff in chemistry. So I remember asking my instructor about it, and he almost went into coronary arrest. Talk about a stupid idea, I'm not going to waste my time. Okay, you don't have to. Well, while, of course, the continents were still drifting. So anyway, that's where the story stayed. And it stayed that way for a long, long time. Actually, it stayed until we started to get information from that have nothing to do whatsoever with continental drift or plate tectonics or anything else. The first source of information came from our knowledge of the ocean bottom. I think you have to realize that up until actually the Second World War, we really didn't know anything about the deep ocean bottom. Taking a geology course early on, I won't tell you when I took the first course, but we were taught that basically from continent to continent, the ocean bottom looked like a billiard table. They thought it was simply flat like a billiard table. Why did they think that? They had no reason not to think that. So anyway, that was the picture, you see. Well, that was up until actually the beginning of the Second World War, but the story actually starts at the end of the First World War. At the end of the First World War, the United States Navy invented sonar. And I think you all know what sonar is. It's this sound reflection technique that we can use to tell the depth of any kind of a body of water. They invented it after the First World War. It was really never used for anything until the Second World War. But in the Second World War, they started to look at the ocean bottom. And the first one they looked at, of course, was the Atlantic, sailing back and forth across the Atlantic, taking profiles of the Atlantic bottom, and they made an amazing discovery out there. They found that out there in the middle of the Atlantic Ocean, there was a mountain range out there. This thing rose from the deep ocean bottom about 15,000 feet below sea level. It came up to usually within 1,000 or 2,000 feet of sea level. In other words, submarine. That's why no one ever knew it was there. Now we know, of course, there are a few places where it pokes its head above water, one being, of course, Iceland. That's a little part of it.